Hey everyone, in this video we're going to introduce polar coordinates for the purpose of simplifying some of our limit calculations. So in the homework we had this limit here where we're trying to see as x and y go to 0 and 0, what happens to, oh my goodness, this amazing fraction. And when we tried to figure out what the limit should be, or if it even exists at all, we maybe tested a couple of different directions. We said, well, what if your x is 0 and the y is not 0? Then you ended up with 0 over y squared, which was 0, which automatically tells us if the limit exists, it better be 0. But maybe the limit doesn't exist, so we tried when y is 0 and x is not 0. In which case we still got 0 over, well, now x to the fourth plus x squared, which is always 0. So that's consistent with what we found above. We've also found, maybe you should try like y equals x. That sometimes can find you a nice contradiction. But when we do that, we end up with, let's see, x to the fourth minus 3x to the fourth over x to the fourth plus 2x squared. And let's see, these are going to combine on the top to give us a negative 2x to the fourth. And then I can cancel an x squared because, of course, I'm going to assume that x is not equal to 0. So I end up with negative 2x squared over x squared plus 2. And as x goes to 0, the numerator goes to 0, and the denominator goes to 2. So as x goes to 0, this goes to 0 over 2, which is 0. So once again, all three directions that we usually like to check, we see we're getting a 0 limit. Now, this doesn't prove anything, right? We have not proved that the limit is actually 0. We simply know that if the limit exists, it's going to have to be 0. And we would like to prove that. Now, we can go through the limit definition and find an open set around 0, 0, such that if you evaluate this function at anything in that open set, you can make it smaller than any epsilon. It's a real pain. And maybe if there's demand, I can make a video where I show a couple ways to do that. But oh boy, it's going to be so much easier using polar coordinates. So let's briefly introduce polar coordinates and then see how we're going to apply it here. So polar coordinates are going to be a way of expressing points in the plane. So typically we have the x and the y axis, and maybe you have some point, and it has an x coordinate, and it has a y coordinate. Right? Call them, say, x and y. Why not? All right, and then we label the point x comma y. Okay, so you're used to doing this. And if I tell you what x is and I tell you what y is, that completely determines which point in the plane we're talking about. And if I give you the point, well, you know what your x and y are. Okay, but there's another way of giving you instructions for how to find this point. So another way to do it is to first say, how far away from the origin is it? Okay, so usually we call that distance r. Now, if I just told you that distance, you wouldn't be able to distinguish between that point or any other point on a circle of radius r, right? They all are r away from the origin. So what I also have to tell you is what angle does this ray from the origin out to the point, what angle does that make with the positive x-axis? Now, you might say, well, if I go around and around and around multiple times, there's actually multiple angles that will work. And that's fine. For the purposes of this discussion, let's just assume our angles will go between 0 and 2 pi radians, or 0 and 360 degrees if you prefer. All right, but the value is, right, once I know this angle, that's going to completely determine where I am going around this circle. So we might call this a rectangular coordinate. And if we write it using the r, so the distance from the origin, and the theta, the angle between this ray and the positive x-axis, then we are going to call that a polar coordinate. All right. A useful piece of information is to know how to convert between rectangular and polar coordinates. So we can find that by observing that we have a right triangle in this picture. And so what can we observe here? Well, first, the height of this triangle, right, is just the y coordinate. So that has height y. And the base of this triangle, right, so this distance here, right, that's just the x coordinate. So that's x. And so, for example, if I write down the cosine of theta, we know that's going to be the adjacent over the hypotenuse. So x over r. And so if I solve for x, then I get x is equal to r times the cosine of theta. So this is a way, once you know the r and the theta, you can produce the x coordinate. Similarly, the sine of theta is going to be y over r, and so y is going to be r times the sine of theta. So if you know the r and you know the theta, you can immediately, using these formulas, write down the x and y coordinates, right? The rectangular coordinates. All right. Now to go backward, let's make another observation. We have a right triangle here. So we have the Pythagorean theorem, which relates the sides of the triangle with the hypotenuse. So we know that r squared is equal to x squared plus y squared. So once we know x and y, the rectangular coordinates, the sum of their squares will give me the square of the radius. And because we're assuming that the distance between the origin and this point is a positive or at least a non-negative quantity, then you can take the square root of both sides. Okay, but usually we'll just write it in this form. Now we also, of course, want to get the theta. And typically in books, they're going to write something like the tangent, right? They'll note that the tangent of theta is y over x. And so then you can use this to solve for theta by taking the arctangent and then figuring out which quadrant you're in. I typically prefer to use cosine instead. That's just my preference. The one difference is when you use the tangent, right? You don't need to know the r; it doesn't show up. To use the cosine, right? You actually need to know the r, but we can use it, right? I mean, this exact formula still works, right? So cosine of theta is still x over r, and so your theta is going to be, well, plus or minus, right? We have to actually see which quadrant we're in, the arc cosine of x over r. Okay, so we have to check, right? So this needs checking, right? You're not quite sure. Okay, and of course that's the same thing with the arctangent as well. You have to check which quadrant you're in. Now there is one teeny little hiccup when, with xy, you tell me the point and I know exactly what the coordinate is, right? In particular, let's look at the origin. You know the point here is, right, 0, 0. If you do this in polar coordinates, well, you know that you're going to be 0 away from the origin if you're at the origin, but the angle is really not clear. In fact, you can just take any angle you like and it won't matter. But this is just a little technical issue, so don't stress about it here. Okay, the things we really want to know, though, for the purposes of solving these limit problems are these three formulas there. Every time I see an x, I can just convert it into r cosine of theta. Every time I see a y, I convert it to r sine of theta. And if I happen to see an x squared plus y squared, that actually is a really nice conversion, right, into r squared. Okay, so let's go back to our limit, and let's rewrite this in terms of r's and thetas. Okay, so let's just write the function for now, right? So x cubed y minus 3x squared y squared over x to the fourth plus x squared plus y squared. All right, so I'm going to convert. So this is a convert to polar now. When I convert to polar, okay, x turns into r cosine of theta. So I'm going to get r cubed cosine cubed theta. I'm also going to multiply it by a y, and that's going to give me an extra r. So it's actually going to be 4 r's now, right? So r to the fourth, then I'm going to have a cosine cubed, and from the y I also get a sine of theta. Okay. Minus, now I get a 3, and okay, x squared is going to give me an r squared. Y squared is also going to give me an r squared, so again I get an r to the fourth. And then I have, let's see, again, it's x squared, so I get cosine squared and a sine squared. So cosine squared theta and a sine squared theta. Over, okay, now I have an x to the fourth, and so I'm going to get r to the fourth cosine to the fourth theta. And then, ooh, wouldn't you know it, I have an x squared plus y squared. I can just write a plus r squared. That's really super nice. Okay, now we can do a little bit of simplification here because you'll notice I have r squared, r to the fourth, r to the fourth, r to the fourth. So I can at least get rid of an r squared from everywhere. So assuming r is not 0, right? Which is what I'm going to assume because when I take this limit, as x and y are going to 0, right? Well, the one place I don't get to make x and y is 0, 0. If my r was equal to 0, well, there's only one place where r is 0, and that's the origin. So I can assume the r is not 0. And so I'm left with, well, okay, before I copy all this, okay, I'm going to tell you guys a little secret. When I'm doing these sort of calculations, I write c instead of cosine of theta and s instead of sine of theta, and it just makes my life so much better. So I can write this as, when I cancel r squared c cubed s minus 3r squared c squared s squared over r squared c to the fourth plus 1. Okay, now I want to take the limit as xy goes to 0, 0. When that's happening, I need my radius to be shrinking. I need r to be going to 0. All right. Now the angle could be anything I like. In fact, it doesn't have to even be some fixed value, right? So I could go along this ray, right? Which maybe even corresponds to the y equals x ray, right? If this was at 45 degrees. But the theta could be changing. All I really care about, though, for sure, is that this r needs to be going to 0. And as it goes to 0, so as r goes to 0, we know that this first term, no matter what theta is, right? These are going to go to something, but I'm multiplying by something going to 0. So this first term goes to 0, and similarly, this second term goes to 0. And so I'm going to be getting 0 in the numerator, and in the denominator, okay, the r is going to be going to 0 here, so it'll kill whatever the c to the fourth is, but then there's a plus 1. So this will be going to 1. Okay, and so we know now that if we switch from rectangular to polar coordinates, we can see that this fraction is going to be going to 0 as the points we choose get closer to the origin, right? As the distance from the origin gets closer to 0. Okay. If you wanted to make this part super precise, where you know that each one of these, r squared times c cubed s, etc., are going to 0 individually, of course, you could use the Squeeze Theorem because you know that sine and cosine, of course, are between 0 and 1, right? We know that. So sine, cosine, of course, you could put powers on them, right? It doesn't matter. Those are always going to be between 0 and 1. Of course, I mean, if they're even powers, it might even be greater than or equal to 0, but that doesn't matter. So we could use the Squeeze Theorem to make this more precise, but it's always the same argument here. Okay, so switching over to polar coordinates, which, by the way, later on in the semester when we start doing multiple integrals, we're going to be switching to polar a lot, particularly when we have domains which are circular in nature. This can also be an amazingly useful trick for proving some limit that are not so easy to do using rectangular coordinates.